So, and then finally, once you have all of those rotational speeds, torques, and powers worked out all the way through the gear train, you can figure out what that pushing force is, right? Remember, torque is a force times a distance, so we can get a force as a torque divided by distance kind of thing, right? So we just take the torque that we just calculated, divide by that radius of the wheel in this case, and that gives us that pushing force. Okay, so before we go into other types of gear shifts for a second, I'll say if we get a chance, I'm going to open a spreadsheet which includes a lot of these kind of gearing calculations, and it also includes the motor calculations that we talked about before. But having said what we just did, a lot of times you'll find a spreadsheet. Either you'll make a spreadsheet or you'll find one online. There are several that are available that help you work through a given transmission system, so you can work out that from or build on the backs of others. I think the calculations personally are simple enough that I would like to work through them myself each time, because out of the grand scheme of things and how much time and effort FRC takes, right, working through these calculations is nothing. It's a blip. And the value of working through them yourself is so much higher than using a spreadsheet. Because you don't really know exactly completely the context of the spreadsheet that you grabbed from somebody else. So I think the best answer is to make your own spreadsheet and understand every step of it along the way. And that's something that we'll demonstrate in a minute. Go back to other types of gears. So we talked about simple gears or spur gears. So here are bevel gears. So if you wanted to transmit power at a right angle, this is a good option. It's still pretty high efficiency. We actually have a setup here. I'm going to show you with a worm gear. So we'll call this the worm and this the worm gear. A couple things to note here is the efficiency is much lower. In other words, it's draggy. Sometimes it can be directional. Right? It wants to go one direction and not the other way, which can be good, because sometimes you want a system that's going to kind of go to a position and kind of lock, or until you can mechanically power it, it won't move. So that draggy nature is sometimes a design benefit. And this is a planetary gear system. And I think probably most of you have experience with planetary gear systems, even if you don't know it. And we have an example I'm going to show you here. So this is, well, actually no, there's no gear system in this. We don't have a gearbox in this one. But this is a 775 motor, which probably a lot of you have some experience with. And there is no additional gearbox in here. This is straight out to a worm gear. And the worm gear drives this rotating shaft here. But often you'll see gearbox put in line with this type of motor, right? Anybody have experiences with those? Wait, next slide. I think I have a picture. I added something. So this type of setup, right? So you can buy these with a certain gear ratio, like a 10 to 1, 5 to 1, a 3 to 1, 7 to 1, whatever you want. And if you want to get to 100 to 1, you can put two 10s together, right? Because it multiplies from one stage to the next. So the reason why I jumped into this from the last thread there on the last slide is that it's a planetary gear system in there, if you've ever taken this apart, right? And why would they use a planetary gear system here? It's very compact. That's it. Yeah, it's really cool, isn't it? If you go back to the last slide, Liam, so you've got all your gears kind of internal. How nice is that, right? Instead of having these external teeth with one gear here and another one over there, everything is like combined, right? Everything's inside the outer ring gear. All right, Liam, could you go another one too? So, what are some transmissions examples? So this is where I'm going to talk about the spreadsheet. I've got I don't know. Go on, Liam. Go ahead. So, next back just for a second. So, I'll because it'll be too distracting to jump back and forth. I'll show you this at the end. But as I said, I prefer to just create a spreadsheet that do the calculations that we've done before. And before I demo that after a few slides, I did want to make a note that we found something very interesting when designing for, well, the previous slide. William, can you go back to the previous slide? So this was 2016, 2017, Steamworks, right? You had to climb a rope at the end. And a lot of people, I think 192, right, used Velcro. So Velcro turned out to be, kind of the killer technology, right? Because you supply your own rope, preferably one that's kind of frayed. It grabs the Velcro nicely, and once it got a couple of wraps, you were good, and you could just go right up. And 190 actually, I remember you would hit the rope, and you had a lot more power and maybe less weight in the robot. So ours was a much slower proposition. So William, jump ahead. So this spreadsheet here, as shown, was to work out the climbing calculation. We were assuming we had one motor turning a drum, right? And we had a certain amount of gearing that we could affect here in the system. So this is an input. You could change your gear ratio, and we've got the motor characteristics. Remember, as I said, you're going to get the maximum motor torque, 0 RPM. You're going to get the free speed RPM, and then you're going to get those current values that we talked about. And then the gear ratio, you're free to vary the gear ratio, right? You want to vary that to solve the problem at hand. And in this case, we had some other things, like I put an overall gear train efficiency in there because there are losses. You're not going to get that out. You can't bring that out of the system completely. And then in this case, the drum diameter was where the rope was wrapping around the drum. And one thing to note there, of course, is after you get a couple of wraps, that diameter changes, right? So it's something tricky to pay attention to. And of course, the robot weight. So based on all of these things, the spreadsheet calculated or presented the torque curve, of the motor, the power curve of the motor, and then it calculates the operating point. And the black, line is the operating point. It could be anywhere in theory, between here and here. Right? If it were here, it would have absolutely, no ability to do any useful external work. And if it were here, the magic smoke comes out. So somewhere in between is where you need to be. All right. So the interesting thing that we learned here was that, we did all our calculations, and we were pretty sure that they were correct, and yet we were not climbing, either not climbing at all or not climbing anywhere near the velocity that we had anticipated. So it was like we were substantially underpowered. We checked the calculations many times, and ultimately, we're convinced that they were correct. You can check them against other spreadsheets and things like that. So there was no error in our calculations, but what was the problem? Well, why was the system, underperforming substantially? Well, as designed anyway, we were just letting the motor, take the current that it wanted, and it was taking an awful lot of current in the beginning, and the voltage on the battery was sagging. So we no longer had that curve, right? So you have this torque curve for the motor, but this is assuming that you're operating at the full 12 volts and everything is ideal. In reality, what happens is when you start to climb and the motor draws all of that current through the internal resistance of the battery, this curve goes bleh, something like that, right? So now you have effectively a much weaker motor. So I guess the lesson with that, as I've seen in other cases, not just in first, is to don't be too cocky about your calculations, because the real world has a way of humbling you, right? And it's better as engineers, I think, to design for understanding the trends. This is better than that. Do this, don't do that, kind of thing. But don't expect to nail physical reality perfectly, right? This is why we prototype and we test. So once we figured that out, we were able to recalibrate ourselves, and maybe we add that second motor up to a larger size or something like that. Okay,
this is the same no matter if you're a rookie team or a veteran team. You run into these things that you haven't anticipated. One good thing that our team always does is give ourselves flexibility in design. So if we're going to use the planetary gears, we always have one stage of chain, so that you can actually change sprockets there and make a significant change without having to redesign your packaging. And so it takes a lot of confidence, sometimes unwarranted, to go straight in with the motor with no way of changing it once you put it in. And so understanding that after 28 years that we've made these same things you're talking about, we learned things. We always try to give ourselves a little design flexibility by having one stage of our transmission which we can modify easily. And about every other year we've had to do that. You know, we have unknown frictions or unknown butterfly wings in Brazil, and something is happening. And so that's a really good point. I don't think everybody got there enough, but do the math, but then be prepared for things that you learn.
So what I think I'd like to do now is skip some of the additional material. I go into a little bit of chains and belts and things like that, because we've only got a few minutes left, and I wanted to, and also probably skip the further deep dive into the spreadsheet. But I will say on the spreadsheet that we created, which I have live, I just basically saved a bunch of tabs. So here's the performance with 1775, driving our climbing motor, with a certain gear ratio. Here it is with another gear ratio. Here it is with a transmission with 2775. Here's with a mini sim. Here's with a full sim. So being able to look at that clearly, even if you're wrong on an absolute basis, you relatively understand this one's better. Do this, go here, do this kind of thing. So what I'd like to do though is I brought this contraption in, so it would be fun to show. This was our intake for last year. So it was intaking they weren't balls, were they? Cargo, is that right? And it also, once we climbed up and we got to the level 3, so I said our legs would go up like this. We had that system to stabilize our pneumatic legs. And this would come down and latch, and then we could lift the front legs, which would put all of the weight on this. So then we had enough traction, and it would drive us forward. So that's just kind of an aside, but we're going to go ahead and we're going to measure some speeds. Well, can you shut that off? Can I marker on that? Or maybe
Yeah, you use markers. The markers work. I mean, they have electronics.
I just want a regular whiteboard. Is that okay?
You have electronics.
I can just go over here, maybe. What's that? So I'll save you the math, but remember the gear ratios are just the ratio of the teeth, right? But it's a little bit subtle in this situation because we have a worm gear, and we can pass it around later, you can look at it later. See, we have a worm gear coming out of the 775.
And this planetary too. Yeah, planetary as well.
Inside.
Yeah.
But there's no gear ratio here.
Oh, there isn't?
No, I don't think so. I don't think there's any planetary.
Yeah, there is.
Is this a stage? Is there a single stage? I don't think so.
Yeah.
Is it?
Yeah.
Okay, that makes sense, because we're measuring like 18,000, and it's not that fast. So why would we be going up? I don't remember what the 775 is needed. But anyway, doesn't matter size. We'll just treat that as a black box. But whatever it comes out of, the motor, you've got a worm driving a worm gear, right? And so the gear ratio, is just a ratio of the number of teeth on the worm. I'm just going to do WG on the worm gear. So that's the big kind of spur gear, divided by the number of something. I don't want to say teeth exactly. It's actually starts, on the worm. And by starts, what I mean is when you have a worm gear, you have to be careful and see how many continuous threads there are, cuts, right? Because if there's one, then every time the shaft turns, it moves the spur gear, or the worm gear to which it's attached, one tooth increment. If there are two separate ones, every time it turns, it's moving it 2 teeth. So you have to keep track of that. So you take my word for it that if this is 50 divided by 2 starts, and the easiest way to figure this out is to use markers and then count carefully, right? And that's 25. But we know that the gear ratio, right, should also be the ratio of the RPMs, right? And which way is it going to go? Which is going faster here? Is it the worm gear here? Which going faster?
Worms are going to go worms, though. Much faster.
So when you can verify this, you know, you can use an optical tack. Anybody use an optical tack? Pretty convenient tool. It's like, you know, you get a $10 optical tack. Hey, guys, can we just move that stuff to a little bit more space for a second? Thank you. Sorry. Oops. So if you run this, then I can have my lovely assistant do the measurements here. You ready? Could you hold that off a little, something like that maybe? Thank you. So we're going to measure the speed at the one.
18,160.
Okay, probably more precision than we're entitled to, but. And then we're going to do the same for the worm gear, which is the same as the whole bar, the shaft, right? Things connected to the same shaft, it's the same, right? Go ahead.
That's 730.
730. Somebody run that math for me. Nobody here has a smartphone, right?
Should be 25 is correct. It's 7.
All right, how close?
It's pretty close.
All right, thanks. We'll just go. You're not going to make me put an approximately equal or anything? All right, so we're not just making it up, right? The gear ratio, you can see, in a very visceral way there. You can either just count the teeth, you can count the rotations. And again, just be careful with the worm gear because it's the number of starts. So it's best to trace around all the way and put like a little dot with a marker every time you have a new thread start, and you can just count how many are in each revolution. And that's the number of starts.
Just look at the end of the
Yep.
arm.
Oh, that's a great idea. Yeah. In this case, I couldn't. There's no way to look at the end, right? But yes, if you have it on a desk or something, you can easily see that, right? Thank you. All right. So we've come to 9:50. So I think I will leave it there. But happy to take any questions or comments that anybody has.
Just a comment on the breaker. So if you actually look at the data sheet, it's actually a little ridiculous when that breaker trips. So if you're running like 125% over the rated current, it'll probably never trip in the match.
Our experience has been that those quick resetting ones have a fatigue life as well,
Yes.
and that the longer you've used them, the more frequently they will trip. The 120, the overall breaker will go to 200 amps.
Right.
But our experience on these is that we never press them past their rated thing because at the end of the season you'll see them chip really quickly. You'll see this jerking like this, and so this is setting and resetting very, very quickly. I think the first time the data works, but after that they seem to get closer and closer and less there. So
Yeah, if you also look at the data sheet, it's a pretty wide range.
Yeah.
You go from like 6 seconds to like 50 seconds or something for a 50% current or something.
you're wise never to design around anything bigger than the.
Oh, I agree, but
Yeah.
if you look at the data sheet, it's a little.
Yeah.
If you're expecting to trip around 40 amps, you might not see it.
You might.
One of those, you can do it. Maybe you should use
Yeah.
it.
Yeah, it is.
Do a brushless motor
Yes, it does.
versus the
I would be happy to have Ken come on. if you don't mind.
Yeah, so,
He's the expert.
just a little bit about motors, so you guys understand we're talking about brushed DC motors. And for example, the curves are totally different with AC motors. Now, don't be mistaken, a brushless DC motor is a DC motor, it operates the same way, except that instead of using symmetrical mechanical commutation, it uses electronic commutation. The other major advantage of a brushless DC motor is that you have a much quicker thermal path from the heating element, which means they can run a lot hotter safely. You can run them at a higher position. There is not a single motor that's available in FRC that can run it at its full power rating without overheating. except for the brushless ones. Because, for example, the sim motors here, their full power is around almost 370 watts, but that's like 60 amps, and they cannot tolerate 60 amps for very long at all. So don't be, it's not nothing magic about brushless motors other than the fact that they have a much easier thermal path for cooling of the electromagnets, and that because they have electronic commutation, they can be phased to produce constant torque, constant speed, but they react the same exact way. The magnets inside don't know whether it's a brushed or brushless, but it's electronic commutation. And so, we're getting more and more of those available now. Some people used them last year. There were a lot of problems with the speed controllers last year. Some people had problems with speed controllers. Anybody use the brushless last year? Brushless? Which one did you use?
The Neos.
Yeah. And did you guys have any problems?
Our battery browns out.
Yeah. So I understand there's nothing magic. If you're going to use more current, it's going to kill your battery quicker.
Right.
But they can produce. They're much lighter for the same. They are lighter for the same power. But one thing I think that Jim would have gotten to is that in transmissions you can do lots of things at speed and torque, but understand that you can never increase the power through transmissions. In fact, everything you put on the end of the motor decreases the power available. Everything you do to it. And so it's wise to look at the physics of a problem when you're lifting and this kind of stuff. Figure out what is the physics to say I need, how much power do I need, and then pick a motor that has that power, and then gear it appropriately. But because you can never increase the power that a motor has. Everything you put on the motor is going to decrease it by the efficiency factor we talked about. But I think that's worthwhile. And we were talking about this earlier that I was going to put together a presentation on brushless DC motors just so people get more comfortable how to run one of those. I expect in the future we'll see more and more of them. But there's nothing particularly magic about them. In fact, they have a different kind of speed controllers. They have to be proprietary speed controllers for them. And that if you think about the way DC motors work with a commutator and brushes, that's what switches the polarity. Now that's done electronically via feedback from the motor to know when the right time to switch the bit on. So, but we didn't get around. Neither of us had time to do that. But next time we'll do it. But you guys had good luck with it, huh?
Yeah, I did find your heat comment interesting though.
Pardon?
I found the heat sink comment interesting. We thought we burned one out.
Yep.
So we measured the resistance on it. On the one we thought was broken and a working one, we got like the one that was broken ran like a 0.3 ohm, and the one that was working ran like a 3 ohm.
Oh, something happened there.
Yeah.
Something got hot.
So we thought we burnt it, but we took it off and they ran it again, and it came back with 3.
Just to understand, the only path for getting rid of heat in a DC motor is through the bearings or through radiation. Because the part that's getting hot is the spinning part. And it doesn't touch anything else. On most, there's 2 different kinds of brushed DC motors, but commonly on the high-powered brushed DC motors, like the one you see on hovercraft and all that kind of stuff, the stator, the part that rotates, only has permanent magnets in it. And so the whole chassis is attached to electromagnets. And so there's a huge heat path to take the energy out of that. Now, DC motors can be made in different ways, but those are the ones that really can handle. That's the reason why you get such ungodly power on those external rotor brushless motors, like on the little skateboards, and all the quadcopters have them. But to my point, I don't think there's any FRC robot now that has an external spinning rotor yet. I don't think. All the brushless DC motors I've seen are still encased, aren't they?
Yeah.
Right, and so you still have some thermal, not as good as the other ones in terms of thermal pass there, but most things are not underpowered with burst. We have all sorts of motors. We've never run out of power anything we've ever done. And frankly, we've never run out of weight since they've changed the last few years. We've never been up against our weight max. It used to be always a problem, but the whole perimeter's gotten smaller over the last half dozen years. So power's not only a problem. And until they go with the lithium power, lithium batteries, I think that having more power is not necessarily a big advantage. Yeah. That's my nice presentation, yeah.
Thank you very much.